Hi, so here we are with the third module for this week. And it's sort of this got a key idea, which is that differential equations are equations too. So in this class, we've thought about derivatives in lots of different ways. We've thought of a derivative as a rate of change. We've thought a derivative as a slope. And we've thought the derivative as a multiplier in the microscope equations. So anytime in a homework or a quiz, I ask a question about those three things, really all I'm doing is asking you to take a derivative. Okay, and so this week we've been looking at various models, and we've looked at models before. And basically in a model, one of the things you'd like to do is you'd like to come up with an equation to tell you how things change. Okay, and well, that's a rate of change, and that's a derivative. And so here are some examples of rates of change equations that we've looked at before, like P prime equals Kp for exponential growth, or I prime equals ASI minus BI for rate of change of infection, or in the Lotka-Volterra model, F prime equals BRF minus df. These are all examples of differential equations. So what do I mean by a differential equation? Well, I mean just an equation which has a derivative in it. And the way that we've been using this is we've been using it to come up with the multiplier we use in our Excel file, so that allows us to compute quantities. So it's just like, it's instructions, it's telling us how to do things. It's very sort of practical kind of thing. So what I want us to do is not to think of differential equations as instructions, but to think of them as equations which have solutions. So that begs the question of what is an equation? So an equation is a mathematical statement about equality. And so, you've got two sides, and the equation is true if the input satisfies that equation and it's false otherwise. Okay, so here's an example of what I mean. So take an equation like x squared equals 4x minus 4. Now 2 is a solution because if we plug in 2 on the left-hand side, we get 2 squared, which is 4. And if we plug in 2 on the right-hand side, we get 4 times 2 minus 4 equals 4. And the left-hand side equals the right-hand side. We have a true statement, so therefore x equals 2 is a solution to that equation. While x equals 1 is not a solution, because on the left-hand side we have 1 squared, and on the right-hand side, we've got 4 times 1 minus 4 is 0. 1 doesn't equal 0, so it's not a solution. And so a differential equation is kind of like in the same spirit as that, except now our inputs are going to be functions instead of numbers. So let's have a look at an example. I think that makes it more clear. So an example of a differential equation would be y prime equals 1 divided by 2y. Okay, and it's an equation, and it's got a derivative in it, so it's a differential equation. Now, y equals square root of x is a solution. What do? We plug square root of x into the left-hand side. The derivative of x to the half is a half x to the minus a half. Down comes the power, we subtract 1. Which is 1 divided by 2 times square root of x. Plugging in y equals square root of x on the right-hand side of that equation, 1 over 2y becomes 1 over 2 times square root of x. The left-hand side is the same as the right-hand side. We have a true statement. Whereas y equals x is not a solution, because the derivative of x then is 1, and that's the left-hand side. And on the right-hand side, we'd have 1 over 2x, and 1 doesn't equal 1 over 2x. So x is not a solution. So in fact, differential equations typically have lots and lots of solutions, infinitely many solutions. For example, in the last problem, square root of x plus c is also a solution for any constant c, and we can just see that by just using the chain rule, right? So we let u equals x plus c, and then we get the derivative is 1 over 2 times the square root of u equals x plus c, and the derivative of x plus c is just 1, so we're just multiplying 1 by that. So again, plug that in, the left-hand side is the same as the right-hand side. Notice that this just gives me another way that I can ask a question about derivatives. So before I could say, what is the rate of change? What is the slope? What is the microscope equation? And these are all ways that I have of asking you to take a derivative. And so this is just another way I can say, is this a solution to this differential equation? And that forces you to take a derivative to solve that question. So in this class, really, we'll be mainly just checking whether something is a solution. We actually won't be constructing solutions. So as I said, there's like infinitely many solutions to a differential equation. So the way that you hone it in on just one function as a solution is you make it an initial value problem. So you give some condition on the solution that restricts what the solution is. So for example, in that problem y prime equals 1 divided by 2y, if we also say that, well, at 0, y should be 5, okay, then we want to find a c that satisfies that initial condition. So we know square root of x plus c works because we've verified that it's a solution. And so then we just plug in 25 for c and 0 for x, and we see that square root of 0 plus 25 is square root of 25 is 5, and that's what y of 0 should be. So again, you verify it by just plugging in, and that's how you go about doing that. Okay, so let's go and do a few more examples. Okay, I've brought this fancy new pen and implement so I can do some writing for you. So for example, here's an initial value problem. Oops, nope, that doesn't work.